In this short lecture video, we're going to examine how the cell voltage in a battery is affected by the ion concentration in the cathode and anode cells. The first battery that we're looking at is the Daniell cell, where zinc ions reduce copper ions. So electrons are flowing from the zinc anode and jumping onto the copper ions in solution. If we crank up the copper ion concentration, go from 1 molar copper ions to 2 molar copper ions, we find that that pull of electrons from the zinc anode increases, and we see that with the cell voltage increased, albeit a modest one, from 1.0 volts when 1 molar ions are present to 1.12 volts when 3 molar copper ions are present. Also, that if the copper ion concentration in the cathode is reduced, the pull on electrons from the zinc anode is also reduced. We find 1.07 volts in the cell with reduced copper ion concentration. So this video will look at calculating voltages under non-standard conditions when ion concentrations are no longer 1 molar. A very good way to get a description of voltage increase or decrease as concentration changes is using Le Chatelier's principle. In the system that we looked at, where zinc is giving electrons to copper 2+, we noticed that when we increase the copper ion concentration, we saw an increase in cell voltage. In terms of Le Chatelier's principle, if you were to increase this reactant concentration, the equilibrium would respond by shifting to the product side. Anytime there's a shift to the product side, we will observe an increase in voltage. Let's examine Le Chatelier and decreasing a reactant voltage. Here is a redox reaction where magnesium is reducing silver ions. If we were to reduce the silver ion concentration, Le Chatelier would think about this change as shifting the equilibrium to the reactant side. Whenever the reaction shifts to the reactant side, we observe a voltage decrease. Both of these examples were looking at the pulling of electrons by the ions in the cathode, but it's also true that the product ions affect cell voltage. If we examine removing magnesium ions from the anode, then in Le Chatelier's language, we would say a decrease in a product ion would result in a shift to the product side. Anytime there's a shift to the product side, we see an increase in voltage. Let's examine this last redox reaction with a picture. So the magnesium donating electrons to silver could be done in this half cell, could be done in this battery where magnesium is the anode and silver is the cathode, and the silver ions are pulling the electrons from magnesium. Well, if I reduce the concentration of magnesium ions, so fewer magnesium ions in the anode, we see an increase in cell voltage as the reaction shifts to the product side. We don't think of magnesium ions as pulling electrons, they're not, but we should think of reducing the magnesium ion makes it easier for magnesium to release an electron and become an ion in solution. So whether I change the ion concentration in the anode or change the ion concentration in the cathode, you can expect to see a change in cell voltage. Let's calculate how concentration affects cell voltage. So the mathematics of this voltage ion concentration change can be found from the thermodynamic relationship of the change in Gibbs free energy from reactants to products under non-standard conditions is equal to the Gibbs energy change when everything is 1 molar under standard conditions. And then RT ln of Q, Q is the reaction quotient, the concentration of products over reactants, allows you to plug in the actual concentration of your ion species. Well, we know that Gibbs energy is related to the cell potential E, and what we want to do is just substitute in minus NFE for delta G non-standard and minus NFE standard in for delta G standard. Doing that gives us a relationship. This relationship can be cleaned up by dividing both sides by minus NF, where N is the number of moles of electrons transferred and F is Faraday's constant. And doing that gives us an equation that relates the cell potential under non-standard conditions to the cell potential under standard conditions. This equation is referred to as the Nernst equation, and on the left-hand side we have the cell voltage when ions are not at 1 molar. It's very similar to the cell it is very similar to the cell voltage when all ions are at 1 molar. And we just plug in what the actual ion concentrations are in the reaction quotient, concentration of products over concentration of reactants. There are a lot of constants in this expression, and if we choose to plug in R as 8.314 and Faraday's constant is 96,500 joules per volt, and if we use a room temperature 298, we find that all those values are 0.0257 volts, and N changes depending on what the reaction is. Maybe 2 electrons are transferred, or only 1 electron, or 6 electrons are transferred in the reaction, but N is the number of electrons transferred. Let's use the Nernst equation and solve for the voltage in a battery under non-standard conditions. The problem that we want to look at examines a nickel half cell, so there's a nickel electrode in a nickel solution, and a palladium half cell, a palladium electrode in a palladium solution, but the palladium is not 1 molar, it's only 0.017. So first, before we use the Nernst equation, we have to decide which of these half cells is the anode and which of these half cells is the cathode. So we find the two cells on a reduction potential table, and always the cell with the highest reduction potential will be the cathode, and the cell with the lowest reduction potential will be the anode, and that voltage will need to be flipped because we're running the reaction in the reverse direction. So having identified who is the cathode and who is the anode allows us to write the chemical reaction where nickel metal is reducing palladium ions to nickel 2 plus and palladium solid. So the Nernst equation will be that we're interested in the voltage when things are not 1 molar. It's going to be close to the voltage when the cell is operating at 1 molar, and then we'll plug in what the actual concentrations are. So let's calculate E cell standard. E cell standard will be the reduction voltage added to the oxidation voltage, where we need to remember that nickel is running in the reverse direction, and so it is plus 0.25 volts for the nickel oxidation, and 1 volt for the palladium reduction. So E cell standard is 1.25 volts. Q in this case, Q is always the reaction quotient, concentration of products over reactant, is the nickel ion concentration, and that's 1 molar, but the palladium ion concentration is now 0.107 molar. And if we plug in those two quantities, the cell voltage under standard conditions and then the concentrations that we're actually using, we're able to calculate the voltage of this non-standard cell. I will caution that plugging into the Nernst equation, lots of values present, and you need to be careful. In evaluating this, I have taken all these values in the correction term and gotten minus 0.052 volts. It's important to go back and think in terms of Le Chatelier's principle. If I reduce a reactant concentration, equilibrium shifts to the left. Every time equilibrium shifts to the reactant side, expect a decrease in voltage, and we see a decrease of 0.052 volts from our equation. If this had been positive and I was shifting to the left, I would know I had made a mistake. So the cell voltage then is 1.2 volts, close to what it was when everything's 1 molar, but we can calculate that change in potential based on the actual concentrations of our ions. Interesting, the Nernst equation helps us think about a battery running out. When a battery runs out, E cell becomes 0. And what happens is this correction term, the concentration of products becomes really high and reactants becomes really low, and this term is equal and opposite to the cell potential at 1 molar. Let's use the Nernst equation in a different way where we know both E cell and E cell standard. This is an interesting way to measure solution concentration. We have a cell that has as the anode the standard hydrogen electrode, and the cathode is copper ions, but not copper ions at 1 molar. They're copper ions that generate a cell voltage of 0.313 volts. If they were 1 molar, the cell voltage would be 0.337 volts. I want you to think about whether this copper ion concentration is greater than 1 or less than 1. This copper ion concentration is less than 1. Had it been greater than 1, this cell voltage would be greater than the standard 0.337 volts. We will use the Nernst equation in order to solve for the concentration of copper ions. We know E cell under the non-standard conditions 0.313, E cell standard 0.337, and we need to find the reaction quotient, Q. That's what we can solve for. We've been given the cell notation for this cell, but it's important in order to get Q to write out the chemical reaction. So in this case, the cell notation says that H2 is donating electrons to copper 2+. So my reactants are H2 and copper 2+, forming copper metal and an acidic solution, forming 2 H+ ions. So writing the reaction quotient now is just products, H+ ions squared, the pressure of H2, and the copper ion concentration. Well, the anode is under standard conditions, so I'm 1 molar for the H+, and I'm 1 atmosphere for the partial pressure of H2, and so numerically I can plug in 1s for the components of the anode, and X is my unknown copper concentration. I could have kept that copper 2+, but I chose to use X. Well, let's plug in everything we know into the Nernst equation. So under our non-standard conditions, we know the cell voltage. If everything were 1 molar, it would be 0.337 volts. And then Q is just 1 over the copper ion concentration. Let's do the algebra to solve for X. First of all, let's just get ln of 1 over X on one side and everything else on the other. And now I'm going to do the math that combines all of the terms on the right-hand side into a single value, so ln of 1 over x equals 1.87. In order 1 over x out of the natural log, I need to take e to both sides, so 1 over x is e to the 1.87, which is 6.49, and then the copper ion concentration is the reciprocal of that, and we find out that the copper ion concentration is 0.15 molar. So in solution, 0.15 molar copper ions gives a voltage of 0.313 volts when compared to the standard hydrogen electrode. This is a very common and a great analytical technique for determining ions in solutions. You can take a probe that's measuring voltage and stick it into a river or a well and measure the ion concentration of a specific ion by reading the voltage that that ion-specific electrode generates. So the idea that changing concentration changes voltage is handled through the Nernst equation, and you will get lots of practice as we work with this concept.